Alright, in this video or series of videos, we're going to look at rational functions. Pretty much cover everything you need to know about them and how to graph them. So first, what is a rational function? Well, earlier, before watching this video, we would have learned about polynomials. A rational function, hence the per ratio, is when you divide two polynomials. So f of x is a rational function if f of x is equal to n of x over d of x, where n of x and d of x are polynomials with no common factors. Alright, we'll talk about that, simplifying. And we have to keep in mind the domain of these functions. A common theme with domain and functions all year has been you can't divide by zero and you can't take the even root of a negative number. So since by nature of rational functions you're dividing, we have to make sure that the denominator is never equal to zero. And if it is, that's okay. We just find those x values and we take them out of our domain. So let's look at a specific example here. All right, all x values for which f of x is defined. That is what the domain of any function would be defined as. All the x values for which f of x is defined. In other words, all the x values where the denominator does not equal 0. So to find the domain, we're going to factor and then find the zeros of the denominator. So this question says find the domain of each rational function below. So there's just one. I forgot to change this part. So just of the rational function below. Then graph the function on your calculator. And then what happens to the graph at the restricted x values. Alright, so let's factor this. So we're looking for two numbers that multiply to 8 and add to negative 6. So that would be negative 4 and negative 2. And all numbers, look for numbers that multiply to negative 12 and add to negative 1. So like x minus 4 and x minus 3. Now, if we were simplifying rational expressions, which we are, we would cancel that out. But it's very important that before we cancel out, we find the domain. Because we're looking for all the x, if we're looking at h of x, alright, if you were to plug 4 in, we would get undefined. Because it would be 0 times 2 over 0 times 1, which is 0 over 0, which is considered indeterminate. It's not a real number, so we would take 4 out of our domain. Alright, even though it cancels out. So this expression has to equal this expression for every value of x you plug in. So if you plug 4 into this expression, you get indeterminate. If you plug 4 into this expression, you don't. You get 2 over 1. You get 2. Alright, but it should be undefined because this right here is just a simplified version of that. So you have to make sure when you plug in certain values for x, you get the same value for y. Alright, so we're going to take 4 out of our domain. Okay, and then also we're going to take out 3 from our domain because that would make this function equal to 1 over 0, which is undefined. So by saying this, you're really saying x belongs to the set of all real numbers except 4 and 3. Okay, now I want to look at what happens to f of x as x gets closer to 0. So in general, we want to know what happens to f of x as x gets close to whatever makes the denominator 0. So if we were to graph this on a calculator, 1 over x would look like this. Alright, now I'm going to graph it at Desmos, and I want us to understand why it has this behavior at the y-axis. Why does it approach infinity on one side and negative infinity on the other, as opposed to as x gets really large, it sort of levels out and equals 0. Okay, so the answer to that question has to do with arithmetic. Alright, a graph is just a collection of x and y values where you take x, an independent variable, plug it in to 1 over x, and then for this particular function, and what it equals is y. So like if you plug in 1 for x, you get 1 for y. Alright, and as you plug in values closer to 0 on the right of 0, so in between 0 and 1, alright, y gets larger because we're dividing 1 by a number less than 1. Any fraction where the numerator is higher than the denominator is going to be a number greater than 1. So as the denominator gets smaller and smaller, so like if you were to plug in like 1/10 into 1 over x, 1 over 1/10 is 10. So that's why it looks like that. And if you plug in 1/100, it would equal 100. Now as you plug in numbers that were greater than 1, alright, y is going to get closer to 0 because now we're taking 1, a constant, and we're dividing it by a larger and larger number. If you had $1, you have $1. If you had to split it with 2 people, you'd have 50 cents. If you had to split it with 100 people, you'd only have 1 penny. Right? The higher the denominator, the smaller that number is going to be. All right, so that's why these asymptotes occur at the domain restrictions. Well, I shouldn't really say that. At the zeros of only the denominator. All right, vertical asymptotes occur at zeros only the denominator because your denominator gets really, really small, and anytime you take a number and divide it by a really, really small number, it's going to get really large. And that's what's happening to this graph here. It's getting really large, and it's showing with this vertical asymptote.